During the Great Banana Rush of the 1950s, Bobo's great-grandpa, Sir Baba Longtail, traveled to Yellow Peel City to collect bananas. In 1953, Baba had 150 bananas in his collection. For the next 3 years, Baba's banana collection grew by 40% each year. Write a model representing the growth of bananas over time. Alright, so Sir Baba Longtail has a collection of bananas, and we're told that the collection grows by 40% each year. Since we're growing by a percentage, we have exponential growth. And that 40% is our growth percentage, which means our growth rate is 0.40. So we have exponential growth, and we're asked to write a model representing this growth, so we can use our exponential growth model. In that model, we have some starting amount, and we multiply it by 1 plus the growth rate for a certain number of years, and that leads to some end amount. So we want to use this model to represent the growth of bananas over time. So what is our starting amount of bananas? That is 150. So Baba starts with 150 bananas, and then he grows this collection by 40% each year. We'll have 1 plus 0.40, and he grows his collection for some number of years. After 1953, remember he starts his collection in 1953, so we can plug in the number of years after that to get our end amount. Now let's simplify this a bit. Let's use n to represent the number of years after 1953, and our end amount of bananas we can call b. So writing this equation with b first, we'll have b equals 150 times and 1 plus 0.40 is 1.40, and we raise that to the nth power. So now we have a model where we just plug in the number of years that the collection grows, and we'll get a total number of bananas. Let's keep working with this model. Calculate the number of bananas in Baba's collection in 1954, 1955, and 1956. Draw a chart of your data. Okay, well, we just created a model for the number of bananas in the collection, so let's use that. In our model, n represents the number of years after 1953. So if we consider n equals 1, this means 1 year after 1953, which is 1954. And using our model, the number of bananas in 1954 would be 150 times 1.40 to the first power. And using a calculator, we would get 210 bananas. So we started with 150 bananas, and after 1 year, we grew to 210. We can continue this with n equals 2. This is 2 years after 1953, which means 1955. And using our model, the number of bananas in our collection would be 150 times 1.40 squared. Using a calculator, we would get 294. And finally, n equals 3 means 1956. So the number of bananas in our collection in 1956 is 150 times 1.40 to the third power. And using a calculator, we would get 412 bananas. And now we're going to put this information on a chart. We'll have our number of years on the x-axis and our total number of bananas on the y-axis. So when n equals 1, which is 1954, we have 210 bananas. So when n equals 1, we can plot approximately 210 bananas. Similarly, when n equals 2, we have 294. So on our chart, we go to n equals 2 and plot 294. And finally, n equals 3, we have 412 bananas. So n equals 3 and 412 bananas. You might notice that our points are slightly curving up, as they should with exponential growth. Let's add one more piece to complete this graph. Baba plans to finish collecting bananas in 1959. Estimate how many bananas he will have in 1959 if he continues collecting at the same rate. So our collection is going to keep growing at 40% each year, so we can use our model. And what does our n have to be in this case? How many years after 1953 is 1959? That would be 6 years. So 1959 means n equals 6. So the number of bananas in our collection would be 150 times 1.40 to the 6th power. And using a calculator, we would get 1,129 bananas. Let's add this piece to our graph. We'll need to add n equals 6 to our x-axis, and we'll need to extend our y-axis quite a bit. And we found out that in 1959, which is n equals 6, Baba will have 1,129 bananas. And now we have a much better picture of exponential growth.